So welcome back for the second day of PQI 2022. I'm Rob Cunningham, the Deputy Director of PQI. I have the great honor of introducing Margaret Martonosi. If you haven't looked online, I'm going to give you just a tiny bit of her background. She is the National Science Foundation's Assistant Director for Computer and Information Science and Engineering. She is leading an organization that has a budget of over $1 billion, and the directorate has the mission to uphold the nation's leadership in scientific discovery and engineering innovation through its support of fundamental research and education. Before she was there, and I guess now because she's on leave, she's at Princeton University, where she's done just amazing research in computer architecture of all types, but I'm particularly focused on the quantum computer architecture work that she's done. I've been a huge fan of her work for many years, not only her papers, but she's taken the time to put a number of really important and impactful presentations online. And so if you haven't seen those, after you see this, I'm sure you're going to want to go off and go do it. So let me start out by welcoming Margaret Martonosi, and I hope that you'll clap with me as well. Thank you.
Good morning, and thank you. It's great to be here. As Rob mentioned, I've been at NSF for about 2.5 years. The vast majority of that has been in Zoom land, and so it's fun to come out and see people in 3 dimensions again. With that, I'm going to give a talk that is, I would say, wearing both of my hats that Rob mentioned. So I lead the SCI's Directorate at NSF, and it's our role there to steward research funding for the broad computer science community. SCI's, NSF fund about 80% of the academic computing research in America. So that's a huge role. And then we work with the other directorates like math and physical sciences and others on interdisciplinary topic areas, of which this is certainly one, quantum. On the other hand, I also have been working on computing research for close to 30 years now. And in that role, I've done a bit of quantum computer architecture work myself. And so this is an interspersing of some of those results just as examples within a broader talk about what NSF is doing on this front. So with that, here we go. So in terms of quantum, depending on who you ask, you might hear different origin stories. I'm guessing that if you're a physicist, this might not be your origin story, but trust me, there's another one. So quantum computing, where does it come from? Why are we pushing on it? One version of the origin story might look like this. Moore's law dates back to 1964, 1965, and it was about this vision for cramming more components onto integrated circuits cost effectively. And that's Gordon Moore and Robert Noyce that you see studying this. Gordon Moore came up with that extrapolation about doubling the number of transistors on chip every 18 to 24 months based on the data you see here. So it's a pretty bold extrapolation. He sat there in 1965 or so, and he said, we'll operate at the lowest cost point on that left-hand side graph. The y-axis there is manufacturing cost per component. The x-axis is the number of components per IC. If you presume that we will always want to be at the lowest cost operating point, then you take the left graph and you can map it onto the right graph. And that's the data that started Moore's law. And I always tell my students to go check this out because it's a pretty bombastic thing to say. So where are we now? Where we are now is that we've stayed on that. It's not a law of physics, right? It's a law really of businesses being willing to invest to make it keep going. And so the orange triangles on this graph are transistor counts from 1970 to nearly the present. The y-axis is units, and note that those are powers of 10 on the y-axis. And these are pulled from real, from databases of real processors that have actually been built. So these are real data points. And the orange shows that up until maybe 5-10 years ago, we were still staying on a doubling curve. But you can see that other related trends are leveling off or changing. Single thread performance has leveled off. clock frequency really leveled off because we hit power limits. And you can also see in the bottom that we're shifting towards using more and more logical cores, more and more parallel processing on chip to make up for challenges that we have in gaining performance other ways. So we're coming to an end on something, and there's a natural question of what's next. And some folks think that for some particular application areas, not for my laptop, not in general, but for some particular application areas, quantum might be a part of what's next. And what I really like to do is to put this in the perspective of even broader timeline. So this graph now starts, that's 1900 on the left-hand side of this x-axis. It's calculations per second per dollar. So this is, again, a y-axis that's basically a measure of cost effectiveness. And it's a y-axis that is, again, going up by orders of magnitude. And so what you can see here is that we've been on a Moore's law-ish kind of trend for way longer than Moore's law. It goes back to other kinds of calculation machines, mechanical machines. The lower left dot that you see there is Babbage's, is an implementation of Babbage's analytical engine. So we've been performance scaling over the decades, but there's just this natural question of what's next. And different people are coming down different paths about what might be next: optical, quantum, DNA, and so forth. So that's origin story number one. Origin story number two is this set of physicists who came together around 40 years ago, including Feynman, to think about problems of how to simulate the physical world. And, the way Feynman put it was, if you try to simulate in detail the physical world, quantum mechanics, on classical computing systems, the literal volume, the state space, would be so large as to be untenable. And so he had this idea to let the computer itself be built out of quantum mechanical elements to obey those laws, and therefore to be a more natural simulation engine, if you will. And this also launched quantum computing. And so we have these different goals and different sort of launch points, and off we went. Where we are now is something like the following. So this is the last 30 years or so, now with some hand-wavy version of number of qubits up the y-axis. And the blue that you see here are a couple of the algorithmic results, early algorithmic results that got a lot of people motivated, in particular Shor's factoring algorithm. And they're mapped by year on the x-axis, and they're mapped on the y-axis by estimates of the number of reliable, and that's an important qualifier, reliable qubits that would be needed to achieve something useful or practical. So those are pretty big counts. And what can we build? Well, that's, this is changing quickly, but, the bottom graph is sort of the number of reliable qubits that's buildable. And the gap is what fascinates a lot of us in the field. It's what's fascinating me, is that there's this huge gap between what algorithms want and what machines can currently do. So in terms of progress, obviously, if you read the news, you know that there's been huge progress lately in building qubits and in building quantum systems. Quantum volume, which is IBM's sort of proposed mechanism for evaluating the capability of a quantum machine, has greatly increased. Qubit counts are better. Gate and noise characteristics are better. The hold time of qubits are better. The connectivity of qubits are better. So we're on a good trajectory, and that yellow line could tip up quite a bit. We're kind of like back in Gordon Moore kind of country, right? Where you have a few data points and we're trying to decide how to draw the line. On the algorithm side, we also have a lot of optimism because new breeds of quantum algorithms keep coming. And while there's a deep focus on the classics like Shor's algorithm, the reality is that there's hundreds of quantum algorithms, with more coming online all the time for quantum simulation, quantum chemistry, quantum optimization. And while not all of them offer exponential speedups, many of them offer the opportunity for practical speedups, and many of them offer the opportunity to implement them on the prototypes that are becoming available, test them out, and learn from them. So this is all good. The gap seems to be closing a bit. But if we actually want to close the gap, then we need to sort of focus in this green area and say, what's next? What work can we do? And there's a range of sort of computer science techniques that might go into that green box. And that's what I'm going to talk to you about today. So, and basically the goal of this work in this green box is to make it narrower, to close the gap sooner, and to see what can we do besides different algorithms and different qubits to close the feasibility point and bring it sooner. Okay, so based on that, I'm going to make an analogy. So we have a big gap here, and you might say we should wait. I often hear people say, the physics isn't ready yet. We should just sit and wait. And I'm going to take you back to 1950. In 1950, this is what a computer looked like. In fact, I think in 1950, this is what a multiplier looked like. So what did we have in 1950? We had algorithms way up high. We had Alan Turing writing a paper that said, can machines think? That's a pretty mind-blowing thing to ask when your computer looks like this. In 1950, we had machines that were made out of vacuum tubes and relay circuits. In 1950, the transistor had been invented, but it was not used in any computer until later that decade. So there's a number of interesting analogies that one can draw here. First of all, we had a big gap in 1950, but we didn't stop thinking about the higher level questions and wait for the physics. So that's one thing that I'll note. The second thing I'll note is that we didn't need to have the winning technology in place in order to make good progress, right? If you were going to pick, quote unquote, pick a winner in 1950, you probably would have picked vacuum tubes or relay circuits. They were all around you. Transistors were not the leading contender in 1950. And so one thing is to not feel obliged to wait to figure out who the winner is. And the second thing is to develop technologies that may work regardless of who the winner is, and to think about it with more abstractions. So from that, you know, we can sort of draw this analogy that we have qubit implementations down low, superconducting qubits, trapped ions, and more. We have algorithms up high, huge gap between them. And so where are we going with this? What happened in today's classical computing world looks something like this. Transistors filled in for vacuum tubes and relay circuits down low. And then we built in a whole abstraction stack that sits above it that helps us manage the complexity and the portability and the other challenges that help us build computer systems today. And so a natural question is, how will we fill the gap for quantum, and what will be in there? And so probably we'd like some different ways of programming for quantum computing. Probably we'd like some compilers and some optimization steps similar to what we've done in classical. Certainly we need good ways to orchestrate classical gate control, orchestrate qubit motion and manipulation, and so forth. So we have a to-do list for the quantum version of the gap, but we don't have a abstraction stack yet. We don't know how it's going to divide out. So this is an intro. This is sort of setting the stage. So my talk said mind the gap, and I'll actually come clean. As I was thinking about it, I think there's two gaps. So one gap is this topical or abstraction gap. That's the blue box of to-do list items. How do we sort of fill in a world of computer and information science and engineering research that fits between the physics down low and the quantum algorithms up high? The second thing is the capability gap, and that's the graph that I showed at the beginning. There's a real algorithms to devices capability gap, and we need to figure out how to navigate that using all that we have available to us. So that's the devices research, the systems and computing research, the algorithms research, all the way up. And so then, because I wear an NSF hat here today, I'll also say, so how can we help, right? There could well be a funding gap. I think we're doing a pretty decent job on funding, but there could well be sort of different funding models that we need to be thinking about to help fill these gaps as well. And so I'll talk a little bit about what we're doing on that front too. So in terms of some ideas, I am not going to dig into any particular research result, but I'm going to throw out a few examples of work that the community has done or that my group has done, just to show for folks who are maybe not familiar with this blue box, just to show the nature of what computer scientists and computer architects take on in this space. And I use these mostly as examples of a set of possibilities. So one thing that a bunch of people in the field have worked on, including ourselves, is different notions of compiling. So from an algorithm to a piece of hardware, how do you do that mapping? How do you synthesize from a programming language to a coordinated set of gate operations that you want to run? And some computer scientists would call this a compiler, just like when you write code and then you run it on your x86 laptop. Other folks might look at it and say it looks more like a design automation, a circuit synthesis step. You take something that you want to achieve and you synthesize it to run as a circuit. Either of those work. They sort of have different mental maps back to the classical world. The kinds of work that we see are people who are generating different configuration constraints. It could be the number of qubits. It could be something about scheduling. It could be something about routing. Mixing that with different attributes of the machine it's running on. That could be connectivity. It could be daily calibration data and so forth. It could be coherence time constraints. And then actually doing optimization problems, formal optimization problems, to come up with good choices. And the reason to do a formal optimization problem rather than heuristics is that these tend to be relatively small machines. So optimization scales okay. And it tends to be the case that this optimization has a fundamental make or break impact on whether you get the right answer or not, and when you get the right answer. And so the ability to do a formal optimization approach actually buys you a lot in terms of the outcomes. What we've shown is that you can get 10x or more improvements over a noise unaware optimized baseline for doing this. And in fact, different versions of this compiler work are showing 10x, 50x, and more benefits over the more sort of generic approaches. These are starting to get implemented, pulled into the different company prototype compilers that are out there, Qiskit and elsewhere. And I think the point that I will speak on behalf of not just my research group, but an awful lot of computer systems folks is to remind you, as you're trying to get your orders of magnitude from the physics, to remind you that we can give you some orders of magnitude too, right? And they are actually, in many cases, orthogonal. They multiply. So the benefits that you give are multiplied by the benefits that we find. And that can be a really effective thing. So this is one. This is knowing about the hardware characteristics, building formal tools to optimize for those hardware characteristics. A couple last things. We've done this for different types of platforms. And in fact, we've done this in ways that are hardware agnostic. So again, back to that notion of we don't need to pick a winner. We have done a single compiler flow that can target either a superconducting qubit or an ion trap qubit by changing some of the configurations. And I think that's useful for people to keep in mind. Second thing I will note, that LLVM IR, that's a lot of acronym crammed up there, and I don't know how many people are familiar with LLVM. It's a widely used compiler framework. It's a compiler framework that helps shape the code that someone wants to install as an app on your iPhone, for example. Apple uses LLVM IR as a way of mapping onto an iPhone. If you go back in time 20 years, the National Science Foundation funded the development of LLVM as an early career research award. We're really proud of that. I 100% know that they did not intend for that to go into quantum computing. But I think one of the wonderful things about research is when you come up with tools and toolkits and ideas that can be mapped to different spaces way past where you thought they were going to go. So that's example one. Example two, instruction set design. So I'm a computer architect. Sometimes when I give this talk, I talk about the birth of computer architecture, which is around the same time as the beginning of Moore's law. Computer architecture is this notion that between hardware and software, there's a single interface that lets software run on any number of implementations of the same within a hardware family, as long as they abide by that interface layer. And the amazing thing about that notion of an instruction set architecture is that it has allowed for scaling, and it's allowed for us to sort of manage complexity decade after decade. The sort of most familiar example for most of you is you're probably, a lot of you, using a laptop that's based on the x86 instruction set. And I would guess that for many of you, that instruction set is older than you are, right? So these are amazingly durable abstraction layers that we've continued to benefit from. And so the natural question for quantum is there going to be a durable abstraction layer? If so, what will it look like? This is in some ways intention. This example is all about letting information flow up and down the full pipeline. I know a ton of stuff about the noise characteristics of the hardware when I'm compiling for it, so relatively little abstraction. This example is kind of the opposite, is can we actually bring some level of abstraction, some level of information hiding to the problem in order to sort of pick a set of gates, a gate set or an instruction set that works well across different scenarios. In this particular piece of work, what we were looking at was acknowledging that on many of the existing quantum computers, for every 24 hours of operation, about 8 of those hours are calibration. So that's kind of astonishing from an energy standpoint, from just a who's going to get to use this machine standpoint. That's a lot of calibration time. And so the goal of this work was to say, can we come up with gates where we design the gate set to keep the calibration costs lower? And one of the things that we observed was that there's sort of different approaches to how gate sets are being laid out. And those approaches, those choices, deeply affect the calibration costs, because the more different gates you have, the more things you have to calibrate. And many of these gates involve some continuous collaboration, some continuous mode of angles and so forth that's causing the calibration times to go way up. So the goal here was to see if we could come up with some sweet spot of enough gates to be expressive, but not so many that the calibration time represented a huge fraction of the runtime. For us in computer architecture, there was a sort of a classic, I won't say war, it was a little bit of a war between so-called reduced instruction set computers, or RISC computers, and complex instruction set computers, or CISC computers, a while back. x86 is an example of a CISC computer. RISC computers include ARM and other ones you may have heard of. And Hennessy and Patterson actually won the Turing Award, our Nobel Prize in Computing, a few years ago, in part for their work on this sort of classic question. So we're asking it again for quantum. And the idea here is to say that there are some machines that have sort of a single type of 2-qubit gate. It's very restrictive for the application. It increases the instruction count in a way that reduces the success rate of the computer, right? Because if you have a lot of operations and each operation has a 3% or a 5% error rate, then pretty quickly, nothing's getting the right answer on these machines. On the other hand, there's instruction sets out there with continuous 2-qubit gates, and there's some examples here. Very expressive, lower instruction counts, which should be good for success rate, but very difficult to collaborate. So again, what we're doing is trying to look for sweet spots between these. What we did is actually sort of explore a full space where we looked at which I-swap-like angles were useful and which C-phase angles were useful, and pick out the most important half dozen or so of those. What you get is that if you go from these continuous approaches to this half dozen or so gate types, you get a 2x reduction in instruction counts, an improvement in fidelity, and you get calibration time that is 2 orders of magnitude less than if you go with the continuous gate set. So, you know, the numbers on this slide, again, every time I get an order of magnitude, I'm pretty happy because I know how hard it is to get an order of magnitude out of the qubit counts. And so this is good, but I mostly use this to show the way of thinking about sort of looking for sweet spots, looking for things that port across multiple platforms and so forth. The third thing, I could give an hour-long talk on this. It's been a lot of fun, but I'm just sort of showing a buffet of how computer systems people think about these things. One of the things that we've been working on lately is cutting quantum circuits so that they fit either into what's simulatable today or into what is runnable on real prototypes today, and then sew them back together again. And if you come from the classical world, this is a very familiar idea. When you do emulation of circuits on field programmable gate arrays, you often have some big circuit, you cut it into chunks that will fit on your FPGA, and you run those, and then you sew the results back together again. I swear, if you are a classical computer architect, this is like so intuitive, but here's the thing. Sewing things back together again in the quantum world has an exponential blow up in reconstruction costs, because the state space of every wire you cut has an exponential cost. So it's still doable, and that's what our work shows. But that classical reconstruction becomes a key step that we have to get past. And so this work is partly about coming up with good places to make the cuts so that things fit on these noisy intermediate scale, the near-term platforms, while also optimizing the classical reconstruction using GPUs. It's using tensor contraction, using many of the things that are getting developed for AI and machine learning supercomputer applications right now as well. So that's sort of a very quick sample platter, if you will, of some things that folks like me work on to fill that blue box of the to-do list between the algorithms and the low-level qubits. And it's built out of an awareness of how those low-level qubits and the systems around them are working and what the trade-offs are, but it's trying to up-level towards higher abstractions from the computer science community. So back to this slide, I'm going to next go into the second half of the talk, where I talk a little bit about what NSF is doing, how we fund for this, and how we look to the future for this. So before you look to the future, wow, this slide has small font. Before you look to the future, it's good to look to the past. And I don't know if you can read the fine-grained text here. These are some grants from 1979, 1982, 1993. Hopefully you can at least see the big blue boxes. Grants that led to the no cloning theorem, grants that led to key insights for metrology, grants that led to the Toffoli gate and quantum Fourier transform. So being at NSF, one of the most rewarding things is to like dig through your portfolio and see how many times you were present at the creation. And so here are a few. Today, we continue to fund, and I'm going to talk about some different funding models. Two awards that we've made that are particularly aimed at quantum computing as opposed to quantum sensing and other aspects of the quantum space are the two you see here. And the goal of these is really to get this mind the gap kind of research rolling in a full stack way, from algorithms, compilers down to devices. And so these are two fairly good sized grants by computer science standards that are rolling along and demonstrating results. Another mechanism that we rolled out a couple of years ago are the Quantum Leap Challenge Institutes. These are $25 million per center over a 5-year period to go big and broad across different aspects of the quantum space. QLCIs are not just for quantum computing, they are for the broader space, quantum sensing, quantum simulation, and quantum computing and so forth. And there's also a strong expectation that these QLCIs will help a lot with the workforce aspects of this, because there's a tremendous opportunity here when it comes to quantum workforce, right? It's a very different space, and we need to think about how to train people to operate effectively in that different space. Because probably if you come out with just a computer science degree, you're not quite ready. If you come out with just a physics degree, forgive me, but I think you're not quite ready either. And so we need to figure out the right ways to mix. It could be that we need master's degree programs. It could be that we need different ways of sort of swapping students across that space. Over two solicitations, these are the QLCI awardees that were made, and you can see that they do span networks and quantum computing and sensing and simulation and so forth. And so we're watching those as they trundle along. Another thing is about workforce itself. And so there's a set of different investments that we've made in this area. One of the ones that came strongly out of the SCI's directorate was called QCIS Faculty Fellows. And it was to recognize that computer science departments really needed to hire quantum folks in order to fill in the blue box and to make the contributions they could. And so NSF made about a dozen awards to give 3 years of bridge funding to departments to specifically hire early career folks who could do quantum related work in a computer science department. So that's one example. And we're in the process of sort of watching those awards. They're getting close to their 3-year mark. It'll be interesting to analyze, as we often do at NSF, analyze what happened with the investment and then decide what's next. It could be that the job market wasn't quite ready to produce the number of quantum CS PhDs needed to fill these faculty positions, in which case we might want to sort of rejigger and try again. Or it could be that all those departments indeed found their faculty and are rolling, and then we have to watch for what happens in terms of the students they graduate. Another program in this workforce area is triplets. So these are a QIS network of triplets, student, faculty, and industry partners that work together on problems. And this is led by Chicago, but these triplets are all over the place. And so it's a way to ensure that the students in this area see the experiential learning side, see the industry side of this space. And then fairly recently, a meeting and a set of workshops have developed a curriculum, the Q12 curriculum idea, which is to bring some key concepts of this into even earlier in people's educational careers, so K through 12, and basically use it as a motivator for how exciting STEM is overall. One very new program is called Expand QISE, and the idea here is to increase the number of universities that are engaged in quantum research, meaningfully engaged, to basically broaden the foundation that America has for quantum research. So the eligibility for this is something that I think was fairly unique when NSF laid it out, but it really sets up universities to play nicely together and to help each other out, we hope. So in particular, to be the lead PI, to be the lead university on an Expand QISE award, you had to have received not more than $5 million of QISE funding in the past 5 years. So this was very deliberately aimed at the folks who aren't doing much quantum yet, but it offered opportunities to partner with other co-PIs at other universities that could very well have deep QISE research experience. And so we literally just made these awards. There's, again, about 11 of them. What we can see are those pairings between different universities, some with a lot of experience and some with less experience, to cover the space and to bring new students in, right? Because if you get new universities, they're going to start spinning up both new undergraduate and graduate curricula in this area. Other funding resources. So I gave you 3 snippets out of my own research, and those snippets 100% wouldn't have been possible without the ability to make use of platforms and prototypes that are out there, for the most part, publicly available. And so I've been personally very grateful for the ability to make use of IBM's platforms that are out there and the other platforms that are out there. What NSF does is try to make that more apparent, those opportunities more apparent for the broadest community. And so we have what's called a DCL, or Dear Colleague letter. It's live right now. You can go use it. It basically says, if you want a student to get up to speed on using the IBM prototypes or Microsoft or the AWS prototypes at Amazon, we will give you money to fund that student. as a supplement to one of your existing NSF awards. And then you can go off and use those cloud-based platforms, either directly through the company, or we also have a cloud bank infrastructure that is basically a front door to a range of cloud connected resources, both classical and quantum, and all of the cloud connected quantum resources actually go through cloud bank too. We have international collaboration supplements where you can sort of co-propose with your colleagues elsewhere and get some global collaborations going in QIS. And a couple of years ago, we also had what's called a convergence accelerator track on QIS to bridge the gap and bring researchers and companies together on some of these research issues as well. So overall, I kind of wanted to show, from the no cloning theorem and the sort of core research that came over the past 40 years up to these different large or center scale investments. The goal is to really build out this space and to bring it to its full potential as its own scientific discovery area and as an area where new technology, new jobs could occur. And so with that, I think I'm happy to pause and take questions. I am happy to be here. I am really curious about whether you're from the computer science side, the physics side, or other. So maybe when you ask questions, if you could give a little bit of a sense of where you are, where you come from, that would be really helpful. Thanks very much for your time and attention.
So we'll take a few questions. Maybe I'll give people a moment. Let me make a comment. In terms of substrates, there's at least one other one that I'm aware of. My mother-in-law was a computer as her first job. And so there are other substrates for computing devices. I hesitate to call my mother-in-law a device, but nonetheless.
I don't know if people don't know what Rob is referring to. Before computers were mechanical, computer was the term that was used for the folks who did the calculations. One who computes is a computer. And especially in the US during World War II, the majority of those were actually women. And the stories that are being told now, 70 years later, are really remarkable. So it's cool that your mother-in-law was one of them.
Yeah, absolutely. All right, questions? Well, maybe I'll start. So I'm a computer and an engineering person. And I was talking to somebody who worries about designing classical computing chips. And they were all excited because there's a bunch of interesting and hard optimization problems that are solved through a number of heuristic-based approaches, but are not necessarily optimal solutions. For those who know about place and route sorts of things, that's what they had in mind. And so his question was, are there things where if we had a quantum computer, we could use the quantum computer to design a better quantum computer? So let me put that question to you.
So people are looking at quantum optimization. So QAOA is a family of algorithms that have to do with quantum optimization in concert. It's an iterative algorithm in which it bounces back and forth between the classical side and the quantum side. And it does a form of gradient descent. And so, yes, you could use it for that. I think it'll be a while. People are mostly thinking about it either for different kinds of physics calculations and simulations, like estimating ground state energy. So there's a kind of tie-in between the quantum chemistry, PQI things, and QAOA. And then people are also looking at it for finance and the optimizations that you'd see in the finance world. I'm not sure whether the scale, so there were two aspects to your question. I thought you were going to say use quantum computers to optimize for classical place and route. I think the scale there would be untenable for a while. Using quantum computers to optimize for themselves. Right now, the qubit counts on quantum computers and the sort of number of optimizations you need to do on quantum computers it's hovering, but it's still small enough that you can actually use full-blown formal optimization and get answers. And some people are comparing formal optimization to heuristics for the quantum side, but you can still get benefits from the full optimization. So I think it's a direction to go, and it may kick in on the quantum side when we get past the current scale we're at.
Great. Other questions? Yeah. All right, you have to tell where you're from and what's your background. Yeah.
I think Margaret Martonosi.
Okay.
But Alex here at the University of Pittsburgh, and I'm working with you at the National Science Foundation for the last couple of years. My question is sort of a problem. So within the space of classical computing, things kind of took off because we were able to create these abstractions and build up gates, and these gates were sort of linear, and you could, make a 2-input, 3-input, 1-input, and that kind of created this nice pathway to build systems that were sort of tracked. Well, it's not like that, right? So if you build a 3-qubit gate, you go from 9 dimensions to 27 dimensions. And how do we deal with this sort of exponential exploding of the problem as we try to scale up just from crawling to walking to answer running?
So that's a good question. So I think quantum bears a fair amount of similarity to synthesizing for FPGAs, in the sense that you have a gate set, or the notion of configurable logic blocks, and you can map onto them. And so that the complexity at the mapping level isn't so hard to me. There's a pretty big intellectual gap of how do you think of quantum algorithms and then map those down, for which my go-to answer would be accelerators. So sometimes when I give this talk, I fess up that this notion that we have, the striated picture of compilers and architectures and so forth, that's really changing on the classical side as well. I could give another talk about that, right? Because we're doing things like TensorFlow and PyTorch that basically go from high-level abstractions and drill all the way down to accelerators that are circuits, right? So my belief is that quantum will be similar. We will come up with accelerator units that are nicely pre-mapped QFTs or this or that, and then map onto them using techniques not unlike what we do for PyTorch, for CUDA, for TensorFlow on the classical side.
Yep, Vincent.
My favorite is physics make line. How would you position your big project from NSF regulation technology? I think my answer probably goes to
So there's so many interagency conversations that occur on these topics. So the question, just to repeat it, was about DARPA's investments in quantum and how that sort of complements NSF's investments, and do we talk to each other? And obviously you didn't mention Department of Energy, but that's another place where there's large scale investments in quantum right now as well. So across that space, we do try to have complementary efforts and coordinated efforts. Actually, this Friday will be QIS Day for the federal government. And at NSF, we will have a whole day of sort of program officers getting together across DARPA, NIST, DOE, NSF, and so forth. So we coordinate through events like that. We coordinate through the national NSTC subcommittees. There is one on quantum, and so NSF has a representative, DOE has a representative. We also have MOUs of collaboration on different aspects of this with DOE. And speaking more broadly outside of quantum, we partner with DARPA and DoD on funding opportunities. Our AI institutes and our cyber physical systems investments have DARPA and DoD partnerships on them. So I think that might not be apparent to the academic world, but we do collaborate. DARPA tends to be deliverables focused, right? You will have your brilliant insights on a quarterly schedule, and you will meet the milestones that you thought of 5 years ago, right? I love DARPA. I have happily received DARPA funding, but it's a different mindset than painting out a pathway of where you think you might go and then seeing where you actually go and having the impact come more organically, which is more of the NSF model. So we sometimes give out no cost extensions. We sometimes give out supplements. In general, we haven't made a call on whether we will, on how many more QLCI competitions we'll do or anything like a renewal. For large facilities, there's a notion of renewals. But for grants at this level, we know that the people with ideas are everywhere, and some of the people with ideas are the ones who already have funding, and some of the people with ideas are the ones who want new funding, right? So we have to come up with a portfolio that's respectful of all of that.
Okay, we have one more. Yep, go ahead, Kaushik.
My question is, so I really like how you mentioned this part between the gap between algorithms and actual implementation on how you say that you just idea and other startups.
Right. So about the quantum resources, by our count, almost everything that people can name is covered through those 3 entry points because of coordinating agreements that the companies have. So for example, Amazon isn't just Amazon. Amazon has a set of companies that they partner with, and their resources are available that way. So I think that's my first answer is you'd be surprised how many companies this covers. My second answer is if there's some company that truly isn't, whose resources are out there and truly not covered by this, send me an email, let me know.
All right, let's thank our speaker one more time.
Thank you.